In the last discussion that we had, we actually observed that the prediction that is coming from the expression 2 gamma s times E, where this is the surface energy and this is the Young's modulus, is actually smaller, much smaller than experimental values of the fracture toughness. And the question is why? And as I mentioned at that time, this is an important aspect of all this discussion because it actually reveals to us a couple of aspects of fracture resistance that can be tuned when we are designing new materials to maximize this fracture resistance. In the next few slides, I'm going to show you exactly the origin of this discrepancy. First, I will very briefly discuss it, and then in a rather detailed way, we will analyze the aspects of the problem that they are important. So, the reason that the Griffith approach has to be modified is that there are other absorption mechanisms, like plasticity, for example. Plastic deformation requires energy, and at least in the context of the stress amplification that we had discussed, so if you have a crack of the size of 2A, we said that the stress at the tip of the crack actually becomes proportional to this factor, where this is the radius of curvature at the crack tip, and this is the half length of the crack. So if this is very large, obviously plasticity should actually take place in the front of the tip of the crack, and that somehow has to be taken into account. And the reason that the analysis that we did before actually did not take this kind of mechanism into account is that we compared two situations, one situation with no crack and another situation with a crack for the same material and geometry. And we said, okay, what's the difference between these two? We did all the game with the elastic energy and the surface energy, and we came up with the formula that included this expression. However, this is not spontaneous. We don't go from here to there. We don't go from no crack to crack immediately. There is a process, and the process actually requires that you have a crack that is progressively increasing. So the process is actually can be explained in the following way. If you have a crack of certain size, you're going to have an area in front of the crack tip, which I denote here with this color, where the material is going to yield. As the crack propagates in its new configuration, the crack is going to have a more or less self-similar area in front of the crack tip that is yielding plastically. And as the crack propagates, there is a wake of the material behind the propagating crack that represents the area that has plastically deformed. So the more the crack propagates, the more energy is required in order to make the material yield in front of the crack tip. And that has to be taken into account. And this is exactly what people try to do in the early stages is, okay, we said before that this is an area where energy goes into for the creation of the new surface of the crack, but we have to include another factor here that represents the plastic energy, the energy to make the material yield plastically as the crack propagates. And in a simplified term, we say this is not just this, there is more. And therefore, the fracture toughness is justified to be larger than the simple expression that we had discussed before. And not only this, actually plasticity is one of the mechanisms that absorbs energy. In fact, there may be others, and we will discuss this in detail. And if you rearrange things, in fact, you can write this ratio and make it equal to this summation of terms that absorb energy, and come up with a new parameter which we call the energy release ratio, which is the more generalized concept that represents all the mechanisms that absorb energy as the crack propagates. And in fact, we call it with the letter G to honor Griffith, who was the one that, in a way, formed the foundation of understanding of fracture in the modern era. I'm going to actually go through a very, very quick discussion of the stress in the front of a crack tip. And instead of going through this for all the possible ways that crack can occur, a crack propagation can occur, I just want to mention that the opening of the crack in a form like this, okay, where the propagation of the crack is actually normal to the direction of the loading, is only one of the ways that fracture can occur. And we call this actually mode 1, which is the opening mode. And I really like this cartoon because it can represent the different ways that a crack can grow. For example, here, the crack can grow under a force which is actually parallel to the plane of the crack and the direction of the propagation. Here we have a force which is actually, this way, it's parallel to the plane of the crack, and the propagation of the crack actually is in the normal direction of the force. So these are called the sliding mode or mode 2 and the tearing mode or mode 3. Anything that I will discuss in the next few slides, in fact, can be presented in an analogous way for all modes, but I will just, and in fact, all the discussion in this class can be expanded to the 3 modes, but I will only discuss mode 1 as the simplest and fundamental mode of failure. Okay, so let's have a look at a quantitative approach to this problem. This problem can be solved mathematically under some relatively strong assumptions. So the first assumption is that the material is actually purely elastic. So there are elastic constants, the modulus and the Poisson's ratio, and the material is isotropic. And so there are mathematical ways of actually analyzing this problem that go back all the way to 1940s. And just to discuss the description of the geometry, I want you to have a look at this schematic here. This is the crack, and this is actually the tip of the crack. So if I put this coordinate system situated with its origin situated exactly at the tip of the crack, and I call this X and this direction Y, I can also use a polar coordinate system because actually it's quite useful. And in that case, I have the position of a point with respect to the origin defined on the basis of the radius and the angle of this distance. So instead of X and Y, I have r and theta, okay? And I will use this coordinates to show you the values of the stress in front of the crack tip. Of course, this is an approximation. The material is not just elastic, it will yield, but for the time being, let's use this approximation as the basis of starting to quantitatively understand what is going on in front of the crack tip. So, the solution of this problem has this form, and these are actually the three stresses that exist in this problem. We have stresses in the x direction, we have stresses in the y direction, and of course we have a stress in the shear of the shear form, and all of them can be written in a very nice and symmetric way. There is a factor that they scale to this factor, and then there is a individual expression for each of them that depends only on the angle theta. So this factor here has two parts. It has the stress intensity factor, K1, and for this problem K1 is nothing else than actually the microscopic force times square root pi a. In the denominator it has the distance from the crack tip in terms of the radius, and you notice that the denominator is actually proportional to square root of r, and because we have r in the denominator, a parameter that can take a value close to 0 or 0, you can see that as r becomes to 0, all the stresses actually tend to infinity. And so we say that in this problem, the crack tip is essentially a singularity point, a point where all the stresses actually tend to infinity. And in fact, the exponent of r, which is here 1/2, is actually the degree of intensity, if you wish, of the singularity. Okay, there are other expressions here with respect to displacements and things like this, and also there are values here for the through thickness stress, but I don't think we need to discuss it at this point, exactly at this point. Just keep in mind this, that is, every stress in the vicinity of the crack tip, first of all, is proportional to 1 over square root of r, and therefore it becomes very high as the position of the point that we are considering is going close to 0. Second, that every stress is actually proportional to the stress intensity factor. So this factor is actually a very important parameter of this problem. It governs, if you wish, the stress intensity in front of the crack tip. I guess that's why they call it a stress intensity factor. And it's the same, exactly the same factor that is actually entering into every stress at the vicinity of the crack tip. Okay, so keep this in mind. The important things are the proportionality of all the stresses to the stress intensity factor, the proportionality of all the stresses to 1 over square root of r, and then the individual geometry forms that give you the precise value for every stress based on the angle theta in the geometry that you see here up on the right. Okay, and similar expressions exist for the other modes. I just don't want to actually discuss them at all at this point. This graph essentially amplifies what I said before, the fact that the stress intensity is actually a key parameter for the fracture problem. plastic zone εδώ. Now that we have a good idea about the stresses in the area around the crack tip, we can start understanding the area and estimating the area where plastic deformation occurs. And the simplest approximation to it is actually to take the value of sigma yy, that is the vertical stress, and go back to the formulas that we had looked at a few slides ago. And if you are careful and you substitute theta equals 0 in sigma theta theta, you will see that actually the vertical stress along the x-axis when theta is 0 is actually of this form. So essentially it is a function like this, and you can see that it tends to infinity as r goes to 0 or x goes to 0. And the easiest thing to do is actually say, okay, it is impossible for this stress to be going to infinity. There must be a limit. And what is that limit? That limit is actually the yield stress. And if you put the yield stress there, you can see that practically any material within this zone, and we can call this zone the plastic zone, any material that is in this zone is essentially plastically deforming. So you can take this guy and put 2pr 1/2 equals sigma y now, where this is the yield stress, and essentially just raise this to square and solve for rp, and you will see that this is equal to actually this term here, which is this formula right here. It is an approximate way of deriving it, and but it gives us an idea of the magnitude of the plastic zone in front of the crack tip. In reality, this zone has actually a special shape, and its shape depends actually on whether you have plane strain or plane stress or plane strain. And in order to understand this, we need to go back and remember actually what is the difference between plane strain and plane stress. And I'll make a parenthesis here to explain this. So plane stress is the situation where typically the thickness of the material is very small. So thickness is essentially much smaller than any other dimension in the material. And in situations like this, the stress is normal to the plane of the material is practically 0. Not only this stress, but also any other stress like the shear stresses that include the third direction. So that is the condition for plane stress. And practically speaking, the strain in this direction is not 0, it's the stress that is 0. On the other hand, we have the situation of plane strain, which is typically the situation where one dimension is actually, I'll call it tib, it's not thickness, but anyway, it's actually one dimension that is actually much larger than the other two dimensions, or there is a specific boundary condition that prevents this length from changing. So in this case, the strain in that direction is 0, and actually every strain also that includes that direction. And the stress is not 0, and for elastic materials, these are actually the corresponding estimates. So these two extremes, the plane stress and the plane strain, correspond to situations where the stress in that direction is 0, or in the other case, the strain is 0. And based in these two situations, we have actually two different estimates for the plastic zone. So one is for the plane strain, and actually one is for the plane stress. And there are two important things to remember here. The first one is actually the fact that for the same K, stress intensity factor, the plane strain, the plastic zone for plane strain is actually smaller than that of the plane stress. Can you see that? Here we divide by 2 pi, and here we divide by 6 pi. So this, the yield zone for plane strain, I guess, is actually smaller than the yield zone for plane stress. Okay? That means if everything else is equal, that is, you have exactly the same material, you use exactly the same dimensions, if you have a plane stress condition, your material will exhibit a higher fracture toughness in plane stress than in plane strain. It's not easy to actually realize this, but the fact that this is larger than that, it means that more work is going to be required here as the crack propagates, and as a result, the fracture toughness of the same material is actually larger in plane stress than it is in plane strain. So this is an interesting complication which we see here for the first time. That is, the fracture toughness of the material is not a true material behavior, but it actually depends on the geometry. And if the geometry leads to plane stress, or is close to plane stress, then the material exhibits a higher fracture toughness than the same material in the geometry that is close to plane strain. The next thing that I want to show you is actually, let me continue recording and open up a new slide here. Oh, come on. Okay, so let's take oops. So we said that the plastic zone is like either 1/6 or actually 1/2 pi of the stress intensity factor divided by the yield stress. Okay, so what we need to realize here is that actually the plastic zone is proportional to K square, which is actually equal to sigma square times pi alpha, whereas this is the half length of the crack. Okay, so the plastic zone is proportional to the stress. Okay, and the maximum value of the plastic zone will be when K is actually equal to K1C, which is the fracture toughness, right? And so if you substitute this here, you will get the maximum of the plastic zone. Okay, and this is actually the magnitude of the zone of the material that will actually be deformed as the crack propagates. Okay, so this is the tip of the crack, this is the plastic zone, and this is the area behind the crack that is actually has yielded plastically. Okay. So to understand this also in a more intuitive way, because sometimes these definitions are not so easy to grasp immediately. If you have a specimen like this is the so-called compact tension specimen, and it is typical in the testing of materials for fracture toughness. Here you see the side view of the specimen, and here you see the view from this direction. Okay, so here we have a very thin specimen, and here we have a very thick specimen. And what you see is that if the material is actually very thin, then it is possible actually for this part of the material to thin substantially. If the material is very thick, this pull into kind of a deformation for the material occurs only on the surface. Only on the surface, where by default it has to be plane stress, right? Because there's no force or stress applied there. But in the internal in the internal part of the material, there is really not the ability of the material to shrink, and this is where you have the plane stress condition. And it is this difference that leads to different fracture modes. Actually, here we usually see a fracture at an angle, while here we see a fracture that is actually parallel to this direction. If you want to see this in 3D, this is a good picture that shows this. Remember that plane stress, right, leads to a larger yield plastic zone, and this is shown here in this diagram. So this is the plastic zone in plane stress, while the plastic zone for plane strain, it's actually smaller, and it's this one here. Okay, so you see the large zone on the surface of the material and the small zone in the middle of the material, and that's exactly what is the full picture of an actual crack, of the plastic zone around an actual crack. So this variation of the fracture toughness with thickness can be seen also here in this diagram, where we plot the fracture toughness versus the thickness of the material. And on top of the diagram, you see here the exact modes of failure of the different specimens. And here in this graph, you see the quantitative variation of fracture toughness, which is actually decreasing as the thickness becomes larger. And there is certain thickness and above for which this value is pretty much constant, and we call this value K1C the plane strain fracture toughness of a material. And essentially this is a value that is independent of the geometry, because for any value larger than this critical one, there's no variation of this property. And so it is this value that we are interested in characterizing when we have a new material, rather than the whole curve, for two reasons. First of all, because we don't want to do a lot of experiments, and second, because if we use this as a parameter, as a material parameter for design, it is a conservative one. And if your material actually is down here, it just has a higher fracture toughness, and it gives you a higher safety factor if you design with a plane strain fracture toughness.